The morning of June 13th, 1944, gun battery position Charlie 7, Dymchurch, Kent, England. Lieutenant Robert Turner stood beside his 90mm anti-aircraft gun, staring at the empty pre-dawn sky with a sense of professional inadequacy that bordered on humiliation. Somewhere in that darkness, travelling at 400 miles per hour, a German V-1 flying bomb was approaching the English coast. His gun crew knew it was coming. Forward observers had telephoned a warning 3 minutes earlier. The characteristic buzzing roar of the pulse jet engine was already audible, growing louder with each second. Yet Turner's gun remained silent, its barrel pointed uselessly toward a clear sector of sky, because conventional aiming methods were utterly incapable of engaging a target moving that fast. The standing orders were brutally simple. Do not waste ammunition on targets you cannot see and cannot track. Wait for daylight when visual acquisition might be possible. Accept that flying bombs will pass overhead untouched during darkness. These orders made tactical sense. They also meant watching German vengeance weapons fly unopposed toward London, carrying 900 kilograms of high explosive toward civilian targets that Turner had sworn to defend. The impotence was maddening. His gun could easily destroy a V-1. The 90mm shell had more than sufficient explosive power. The proximity fuse recently introduced from America would detonate automatically within 70 feet of the target, eliminating the need for direct hits. The weapon, the ammunition, and the trained crew were all present and capable. What was missing was the ability to aim in darkness at a target moving faster than any aircraft his crews had ever engaged. What Turner did not know that morning was that 70 miles away, a civilian engineer named Louis Strang was completing an unauthorized modification to an obsolete radar system that would revolutionize V-1 defense within weeks. Strang's illegal improvisation, conducted without official approval or proper channels, would transform the SCR-268 from a forgotten relic into one of the war's most effective defensive weapons. The story of how American industrial pragmatism and one engineer's refusal to accept limitations would change the mathematics of London's survival was about to begin. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The crisis that brought Lieutenant Turner to a gun position on the Kent coast had its origins in German desperation. By June 1944, the Third Reich faced certain strategic defeat. Allied armies were consolidating their Normandy beachhead. Soviet forces were preparing their summer offensive that would destroy Army Group Center. German cities were being systematically destroyed by round-the-clock bombing. Adolf Hitler, watching his 1,000-year Reich crumbling after just 12 years, demanded retaliation weapons that would restore German strategic initiative. The V-1, designated Fieseler Fi 103 by its manufacturers and Flak Zielgerät 76 by the Luftwaffe, represented Germany's answer to military desperation. The weapon was elegantly simple in concept. An airframe 25 feet long carrying an 1,800-pound warhead, propelled by an Argus pulse jet engine that produced a distinctive buzzing sound audible for miles. The guidance system consisted of a magnetic compass, a simple gyroscope, and a mechanical counter connected to a small propeller in the nose. When the counter reached a preset number corresponding to the distance to target, the V-1 would dive toward the ground and detonate. No pilot was required. No trained crew was needed. The weapon could be mass-produced in factories using semi-skilled labor and launched from simple ramps that took days rather than years to construct. Production had begun in March 1944 at the Volkswagen plant in Vorlesleben, where slave labor from concentration camps assembled the weapons under brutal conditions. By June, German industry was producing over 300 V-1s second weekly, with plans to increase that rate to 1,500 per week. The mathematics were grimly favorable for Germany. Each V-1 cost approximately 5,000 Reichsmarks to produce, roughly equivalent to $2,500 American. A single Lancaster bomber cost 42,000 British pounds, approximately $170,000. If V-1s second forced Britain to divert resources to defensive measures, if they terrorized civilians and disrupted war production, if they simply made the cost of continuing the war psychologically unbearable, then Germany might achieve through terror what it could no longer accomplish through military victory. The first V-1 fell on British soil at 4:18 in the morning on June 13th, 1944, impacting at Swanscombe in Kent. By dawn, 9 more had struck targets across southern England, 4 of them reaching London. The British government, which had been anticipating the German vengeance weapon campaign through intelligence reports, immediately recognised the scale of the threat. Duncan Sandys, chairman of the War Cabinet Crossbow Committee responsible for countering German long-range weapons, received initial damage assessments with growing alarm. These were not isolated terror attacks. This was the beginning of a sustained campaign that could deliver thousands of tons of high explosives to British cities with minimal cost to Germany. The military problem was unprecedented. Traditional air defence doctrine assumed that attacking aircraft could be detected by radar, tracked visually or electronically, and engaged by fighters or anti-aircraft guns using standard fire control methods. The V-1 violated every assumption underlying that doctrine. It flew too fast for visual tracking to be effective. It flew too low, typically at altitudes between 2,000 and 3,000 feet, for long-range detection by most early warning radars. Most critically, it flew without variation in speed or altitude, maintaining a straight course toward London with mechanical precision that made it both predictable and nearly impossible to engage using conventional methods. Fighter aircraft achieved some success. Spitfire Mark 14s, specially modified Tempest fighters, and American P-51 Mustangs could catch V-1s second in flight and destroy them with gunfire, or by using their wingtips to flip the flying bombs into uncontrolled tumbles. But fighter interception required daylight, good weather, and considerable fuel expenditure. Each successful interception consumed resources and risked pilots in a war where both were increasingly precious. The mathematics were concerning. If German production reached 1,500 V-1s second weekly, and if even half of those reached English airspace, fighter interception alone could not provide adequate defence. Anti-aircraft guns represented the more sustainable solution. Britain had developed formidable anti-aircraft defences during the Blitz, with gun belts protecting major cities and industrial centres. These defences had been built to engage manned bombers flying relatively predictable courses at moderate speeds. The Luftwaffe bombers of 1940 and 41 typically flew at speeds between 200 and 250 miles per hour. Gun crews had time to acquire targets visually, track them manually, and fire barrage patterns that would force bombers to fly through predicted kill zones. The V-1, travelling at 400 miles per hour, rendered these techniques obsolete. A flying bomb could cross the effective range of an anti-aircraft gun in less than 30 seconds. Manual tracking was impossible. Visual acquisition at night was futile. The British response was characteristically systematic. Within days of the first V-1 attacks, General Frederick Pyle, commanding Anti-Aircraft Command, received orders to reorganise southern England's defences, specifically for flying bomb interception. Operation Diver, as the defensive campaign was designated, would concentrate anti-aircraft guns in a coastal belt where flying bombs could be engaged before penetrating inland. The plan was conceptually sound. Its execution, however, depended entirely on solving the fire control problem. How do you aim a gun at a target you cannot see moving faster than you can track? The American solution arrived not through official channels, but through the desperate improvisation of engineers who understood that existing equipment, properly modified, might serve purposes never intended by its designers. The SCR-268 radar had been developed by Bell Laboratories in the late 1930s as America's first mobile fire control radar. The designation stood for Signal Corps Radio, Unit Number 268, a bureaucratic label that concealed revolutionary technology. When introduced in 1940, the SCR-268 represented cutting-edge military electronics, capable of detecting aircraft at ranges exceeding 20 miles and providing range, azimuth, and elevation data accurate enough to direct searchlights or guns. The system consisted of a transmitter operating at frequencies between 205 and 215 MHz, a receiver with sufficient sensitivity to detect reflected pulses from aircraft at operationally useful ranges, and a display system that showed target position to operators who manually tracked the contact. The radar antenna, mounted on a trailer for mobility, could rotate through 360 degrees and elevate through 90 degrees, providing complete hemispherical coverage. When integrated with an M4 gun director, an electromechanical computer that calculated firing solutions based on target position and velocity, the SCR-268 could, theoretically, direct anti-aircraft guns with unprecedented precision. By 1944, however, the SCR-268 had been largely superseded by more advanced systems. The SCR-584, operating at microwave frequencies with automatic tracking and superior accuracy, had become the standard American fire control radar for heavy anti-aircraft batteries. The SCR-268, with its lower frequency, manual tracking, and relatively limited accuracy, had been relegated to training duties and secondary defensive positions. The War Department considered the system obsolete for frontline service. Several hundred sets sat in storage depots, awaiting either scrapping or transfer to less critical defensive positions. The British, desperate for any equipment that might improve V-1 defences, had accepted a shipment of SCR-268 units as surplus materiel, with no particular expectations of their effectiveness. Louis Strang, a civilian electronics engineer working under contract to the British Ministry of Supply, had been assigned to integrate these American radar sets into the coastal gun belt being established for Operation Diver. Strang's background was unusual for someone working on military fire control systems. He had spent the 1930s designing radio navigation equipment for commercial aviation, work that gave him deep understanding of radio frequency propagation and precision measurement techniques. When war came, his expertise made him valuable to the military electronics development programs that were transforming warfare. By 1944, he had worked on radar projects ranging from airborne intercept systems to ground-based early warning networks. The SCR-268 assignment appeared routine. Install the radar units at gun positions along the Kent coast, integrate them with British gun directors, train operators in their use, and move on to the next project. Strang began the work with professional diligence, setting up the first installations in early June. Almost immediately, he recognized a fundamental problem. The SCR-268, as designed and built, was inadequate for the V-1 defense mission. The system's manual tracking required operators to continuously adjust azimuth and elevation controls to keep the target centered on their display. This worked adequately for tracking bombers that maintained relatively constant speed and course. It failed completely when attempting to track V-1s that crossed the radar's coverage area in seconds, moving too fast for manual tracking to maintain continuous lock. The gun directors connected to the radar required continuous target position updates to calculate firing solutions. If the radar lost track even briefly, the gun director's predictions would become inaccurate within seconds. Against a target moving 400 miles per hour, inaccuracy measured in seconds meant missing by hundreds of yards. Strang watched gun crews attempting to engage V-1 using SCR-268 direction and saw the brutal mathematics of failure. Shells bursting in empty sky behind flying bombs that had already passed through the predicted impact point. Gun layers manually cranking their guns to follow director commands that were obsolete before they were executed. Ammunition expended with no results except confirming that the existing system could not perform its assigned mission. The official response would have been to request more advanced radar equipment, perhaps SCR-584 units diverted from other defensive positions, and to wait for proper installations and training. Strang, watching V-1 fly unopposed toward London night after night, chose a different path. He would modify the SCR-268 to perform functions its designers had never intended, using techniques that violated normal military procurement procedures and technical standards. The modifications he conceived would require bypassing safety interlocks, overriding designed limitations, and operating the equipment beyond its rated specifications. In peacetime, such actions would have ended his career and possibly resulted in criminal charges. In June 1944, with flying bombs killing British civilians nightly, Strang decided that official channels could wait while he demonstrated what might be possible. The key limitation of the SCR-268 was its tracking rate. The manual controls allowed operators to slew the antenna at speeds adequate for following conventional bombers, but insufficient for tracking V-2. Strang recognized that the tracking rate limitation was not fundamental to the radar's electronics, but rather a deliberate design choice to prevent operators from slewing the antenna so rapidly that they would lose track of targets. The safety interlock that limited tracking rate could be bypassed. The servo motors that drove the antenna could operate at much higher speeds if commanded to do so. What Strang proposed was effectively hot-rodding a military radar system, removing limiters and governors to extract performance never intended by the original design. The first unauthorized modification was completed in a single night shift at gun battery position Charlie 7, the installation where Lieutenant Turner commanded. Strang and two technicians who understood what he was attempting worked through the darkness of June 14th, bypassing the tracking rate limiters and recalibrating the servo control circuits. By dawn, the modified SCR-268 could slew its antenna at speeds 3 times faster than the original design specification. The tracking operators, initially skeptical that faster antenna movement would improve anything, discovered that they could now maintain continuous lock on V-2 crossing their coverage area. The radar could track fast enough to keep up with the target. The second modification addressed a different problem. The M4 gun director connected to the SCR-268 calculated firing solutions based on target position and velocity, predicting where a shell would intersect with the target's future position. This calculation required accurate measurement of target speed, which the standard SCR-268 provided by measuring the rate of change in target range. For conventional bombers flying relatively stable courses, this method worked adequately. For V-2, which maintained absolutely constant speed, Strang realized that the gun director could be fed a preset velocity value that would be more accurate than measured speed calculations. This modification required rewiring the interface between radar and gun director, inserting a fixed velocity input that would override the measured speed calculations. The technical risk was significant. If the preset velocity was inaccurate, or if the radar was inadvertently used to track aircraft with different speeds, the gun director's predictions would be completely wrong. Strang calculated the V-1's speed as precisely as existing intelligence allowed, determined that variations in flying bomb velocity were small enough to be negligible, and hardwired a speed value of 390 miles per hour into the director interface. The modification took 3 days to complete and test. When operational, it provided gun directors with velocity data more accurate than any measurement system could achieve because it eliminated measurement error entirely. The third and most controversial modification addressed the radar's accuracy limitations. The SCR-268 had been designed to provide target position data accurate to within 50 yards at typical engagement ranges. This was adequate for directing searchlights and marginally acceptable for gun laying against large bomber formations. Against individual V-2, 50-yard accuracy meant that predicted shell burst positions would be systematically offset from actual target positions by distances greater than the lethal radius of proximity-fused shells. Strang needed better accuracy from a system that was already performing at its designed limits. The solution he conceived was technically elegant but practically dangerous. The SCR-268's accuracy was limited primarily by the timing precision of its pulse circuits and the resolution of its display system. Both limitations could be addressed by increasing the system's pulse repetition frequency, sending out more radar pulses per second to obtain more frequent position updates. The original design used a pulse repetition frequency of 400 pulses per second, a value chosen to balance accuracy against power consumption and component heating. Strang calculated that increasing the PRF to 600 pulses per second would improve accuracy by approximately 30%, while remaining within the transmitter's thermal limits, provided that duty cycle was carefully monitored. The modification required replacing timing circuits in the transmitter and recalibrating the display systems. More concerningly, it required operating the transmitter tubes at power levels and duty cycles beyond their rated specifications. Tube life would be significantly reduced. The risk of catastrophic failure during operation would increase. In normal military service, these factors would make the modification unacceptable. Against V-1s second targeting London, Strang decided the risks were justified. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By June 20th, 1944, gun battery position Charlie 7 possessed an SCR-268 radar system that bore little resemblance to the unit that had been delivered from American surplus stocks. The tracking rate had been tripled through removal of safety limiters. The gun director interface had been rewired to use preset velocity data. The transmitter was operating at increased pulse repetition frequency well beyond design specifications. The modified system was, by any official standard, operating illegally, outside its rated parameters, and in violation of normal military, technical standards. It was also the most effective fire control system available for V-1 defense on the English coast. Lieutenant Turner, who had spent a week watching flying bombs pass unopposed over his position during darkness, received briefing on the modified radar with considerable skepticism. Civilian engineers, in his experience, promised capabilities that rarely materialized in actual combat conditions. The idea that an obsolete American radar system, modified without official authorization, would somehow solve the V-1 tracking problem seemed optimistic at best. Nevertheless, Turner ordered his gun crews to conduct live fire exercises using the modified SCR-268 for fire control. What happened during those exercises would change British defensive doctrine within days. The night of June 21st, 1944, gun battery position, Charlie 7, Dymchurch, Kent. The alert came at 2200 hours. Forward observers reported a V-1 launching from the Pas de Calais, probable track toward London, expected to cross the coastal gun belt in approximately 8 minutes. Turner ordered his crews to battle stations and watched as the SCR-268 operators began their search pattern. The radar, operating at its modified pulse repetition frequency, provided noticeably crisper returns than Turner had seen during previous operations. The operators, now familiar with the increased tracking rate capabilities, reported confident acquisition of the target at a range of 12 miles. What followed was unlike any anti-aircraft engagement Turner had witnessed in 3 years of operational command. The SCR-268 tracked the V-1 smoothly across its approach, the increased slewing rate allowing operators to maintain continuous lock without the target breaks that had plagued earlier attempts. The gun director, receiving the preset velocity data Strang had hardwired into the interface, generated firing solutions with confidence intervals that had never been achievable when measuring V-1 speed in real time. The 4 90mm guns slaved to the director moved in synchronized precision, their barrels elevating and traversing to track the flying bomb's predicted position. At a range of 8,000 yards, with the V-1 clearly audible but invisible in the darkness, Turner gave the order to fire. The guns spoke in rapid sequence, hurling proximity-fused shells toward a point in space where mathematics predicted the target would be in 4.2 seconds. The shells, each containing a miniature radio transmitter that would detonate the explosive charge when passing within lethal radius of any reflective target, arced upward into darkness. Turner counted seconds automatically, a habit from countless engagements. At 4 seconds, the eastern sky lit with a brilliant flash, followed immediately by a secondary explosion that was unmistakably a V-1's warhead detonating. The gun position erupted in celebration. Crews, who had spent a week watching flying bombs pass untouched while they stood helplessly at their weapons, had just achieved a direct kill in complete darkness against a target moving 400 miles per hour. The modified SCR-268, operating outside its design specifications with unauthorized modifications that would never pass official review, had performed exactly as Louis Strang had calculated it would. The mathematics of V-1 defense had fundamentally changed. Word of the successful engagement spread through anti-aircraft command with remarkable speed. General Frederick Pyle, commanding officer of all British anti-aircraft defences, received Turner's after-action report within hours. The implications were immediately clear. If the modified SCR-268 could achieve kills in complete darkness against V-1s second, then the entire coastal gun belt, could operate with 24-hour effectiveness rather than being limited to daylight engagements. The mathematical advantage shifted decisively toward the defence. A flying bomb that required 8 minutes to cross from the French coast to London could be engaged continuously throughout that flight time, multiple gun batteries firing calculated salvos based on precise radar tracking. Pyle's response demonstrated the flexibility that characterized British military administration at its best. Rather than demanding investigation into unauthorized equipment modifications or insisting on formal testing and approval procedures, he ordered immediate replication of Strang's work across all SCR-268 installations in the coastal gun belt. Louis Strang, the civilian engineer who had technically violated military technical standards, found himself promoted to Chief Technical Officer for Operation Diver Fire Control Systems, with authority to modify any radar equipment he deemed necessary for mission effectiveness. The message was unambiguous. Results mattered more than procedures. Saving London mattered more than technical orthodoxy. The crash program to modify remaining SCR-268 units began on June 22 and continued around the clock for the next 2 weeks. Strang established a workshop at RAF Manston where technicians worked in shifts, processing radar units through standardized modification sequences. Each unit underwent the same alterations that had been field tested at battery position Charlie 7. Tracking rate limiters were bypassed or removed entirely. Gun director interfaces were rewired for preset velocity input. Transmitters were recalibrated for increased pulse repetition frequency. The work required precision and careful documentation, because each modification had to be exactly replicated across dozens of units to ensure consistent performance. The technical challenges were substantial. Many SCR-268 units had been in storage for months, their components deteriorating from humidity and temperature cycling. Vacuum tubes required replacement. Servo motors needed lubrication and realignment. Antenna systems had to be checked for any mechanical wear that would degrade tracking accuracy. Strang's team discovered that approximately 30% of the stored radars required extensive repairs before modification work could even begin. The pressure was relentless. Every day of delay meant V-1s second reaching London without adequate defence. Every radar unit that remained unmodified represented a gap in the defensive coverage. By July 1, 1944, 23 modified SCR-268 systems were operational in the coastal gun belt, deployed at intervals calculated to provide overlapping coverage across the primary V-1 approach corridors. The results were immediate and dramatic. Anti-aircraft guns, which had achieved minimal success during the first weeks of the V-1 campaign, suddenly became the most effective defensive measure available. Statistics compiled by Anti-Aircraft Command documented the transformation with numerical precision that left no doubt about the modified radar's impact. During the period from June 13th through June 28th, before widespread deployment of modified SCR-268 systems, anti-aircraft guns in the coastal belt destroyed an average of 24 V-1s second per day, representing approximately 17% of flying bombs entering the gun belt's coverage area. The ammunition expenditure rate was 11,000 rounds per kill, a figure that reflected the difficulty of engaging targets that could not be effectively tracked. Many gun batteries simply fired barrage patterns into areas where V-1s second were reported, hoping for lucky hits rather than achieving aimed fire. The period from July 1st through July 15th, with modified SCR-268 systems operational, showed radically different statistics. Anti-aircraft guns destroyed an average of 68 V-1s second per day, representing approximately 46% of flying bombs entering the coverage area. The ammunition expenditure rate dropped to 2,500 rounds per kill, a four-fold improvement in efficiency. More significantly, the night interception rate, which had been nearly zero before radar modification, now matched daylight performance. The V-1 campaign, which had relied partially on darkness to protect flying bombs during transit, lost that advantage completely. Lieutenant Turner, whose battery had achieved the first kill with modified radar, watched the statistics accumulate with professional satisfaction, tempered by awareness of what they represented. Each V-1 destroyed over Kent was a V-1 that did not reach London. Each successful engagement was approximately 6 civilians who would not die in rubble when 900 kilograms of high explosive detonated in a residential area. The mathematics of defense had become the mathematics of lives saved, quantifiable and undeniable. The German response to improved British anti-aircraft effectiveness revealed how completely Allied defensive measures had surprised Luftwaffe planners. Intelligence assessments compiled by Flak Regiment 155, the unit responsible for V-1 operations, showed consistent underestimation of British defensive capabilities. German planners had calculated that approximately 70% of launched V-2s would reach London, based on assumptions about British fighter and gun effectiveness, derived from earlier bombing campaigns. The actual figure, after modified SCR-268 deployment, was closer to 30%, a shortfall that forced significant revisions to the entire vengeance weapon strategy. Major Werner Baumbach, commanding V-1 launching operations in the Pas-de-Calais, reported with growing frustration to Luftwaffe headquarters that British anti-aircraft defences had achieved impossible effectiveness. His after-action reports, captured after the war, documented confusion nearly identical to what German radar operators had experienced when first encountering Allied jamming. The British are destroying our flying bombs at rates that suggest radar-directed fire of unprecedented accuracy. Night kills equal daylight kills, indicating fire control systems that operate independently of visual acquisition. We are losing weapons at rates that make the entire campaign economically unfavourable. The economic calculation was brutal. Germany was expending enormous resources to produce V-2. Slave labour in underground factories worked under murderous conditions to assemble the weapons. Scarce materials, including high-grade aluminum and specialised electronics, were diverted from aircraft production. Launch sites required construction and maintenance under constant threat of Allied bombing. If 70% of flying bombs reached London, the terror effect and disruption might justify the costs. If only 30% reached their targets, the V-1 was simply an expensive way to waste resources that could have been used more effectively elsewhere. The technical evolution of the modified SCR-268 continued throughout the summer of 1944 as operators gained experience and engineers identified further improvements. Louis Strang established a feedback system where battery commanders reported performance issues and suggested modifications directly to the Manston workshop. This created a continuous improvement cycle that kept the radar systems evolving faster than German intelligence could track. One significant enhancement involved the gun director interface. Strang's original modification had hardwired a fixed velocity value of 390 miles per hour, based on early intelligence about V-1 performance. Actual measurement of destroyed flying bombs revealed that V-1 velocity varied between 380 and 410 miles per hour, depending on fuel load, wind conditions, and manufacturing tolerances. The solution was an adjustable velocity input that allowed gun directors to be set for the specific V-1 speed observed in each engagement. Operators learned to estimate flying bomb velocity based on the characteristic sound of the pulse jet engine, a skill that developed through repeated exposure. Faster V-2 produced a higher-pitched buzz. Slower ones generated a deeper throb. Experienced operators could estimate velocity to within 5 miles per hour by ear, allowing them to adjust the gun director setting before engagement began. This combination of electronic fire control and human sensory judgment produced results that exceeded what either system could achieve independently. The antenna tracking modifications also evolved through operational experience. Strang's initial bypass of tracking rate limiters had tripled the antenna slewing speed, but some operators reported difficulty maintaining smooth track on V-2 at maximum range, where small angular movements translated to large lateral target motions. The solution involved variable rate control, where operators could select from 3 tracking speeds, depending on target range and geometry. Close-range, high-speed targets required maximum slewing rate. Long-range targets needed slower, more precise tracking. The modification added complexity but significantly improved tracking smoothness across all engagement scenarios. The most technically adventurous modification involved integrating the SCR-268 with the new Mark 8 gun predictor, a sophisticated analog computer that had just begun reaching British anti-aircraft batteries in mid-1944. The Mark 8 represented the pinnacle of mechanical computing technology, capable of solving the ballistic equations for anti-aircraft fire with accuracy that exceeded earlier predictors by substantial margins. The problem was that the Mark 8 had been designed to work with the British Good Luck Mark III radar, and its input interface did not match the SCR-268's output signals. Strang spent 3 days in July analyzing the interface incompatibility before developing an adapter circuit that could translate SCR-268 position data into the format expected by the Mark 8 predictor. The adapter, essentially a custom-built analog computer in its own right, performed coordinate transformations and signal conditioning that allowed the two systems to work together despite their fundamentally different designs. The combination of modified SCR-268 and Mark 8 predictor produced fire control solutions of remarkable accuracy, reducing the ammunition expenditure per kill to approximately 1,800 rounds by late July. The human element in this technological success deserves emphasis. The modified SCR-268 was not an automated system like the American SCR-584 that could track targets and direct guns without human intervention. It required skilled operators who understood both the equipment's capabilities and its limitations. The tracking operators, who manually controlled antenna position, had to anticipate V-1 flight paths, leading their targets slightly to maintain smooth track. The gun directors, who interpreted radar data and set firing solutions, had to recognize when tracking quality degraded and abort engagements rather than waste ammunition on poor data. Sergeant William Matthews, a radar operator with No. 3 battery at Dymchurch, described the skill development process in letters home that were preserved by his family. Learning to track V-1s second was like learning to shoot fast-moving game birds. You don't aim where the target is, but where it will be. The radar shows you current position, but your hands on the controls must move to where the flying bomb is going. It took perhaps 24 engagements before the motion became instinctive. Now I can maintain track on a V-1 crossing my coverage at 400 miles per hour without conscious thought. The machine and I work together, each compensating for the other's limitations. This human-machine collaboration represented a different philosophy from the American approach to fire control automation. The SCR-584 eliminated human reaction time from the engagement cycle by automating tracking and firing solutions. The modified SCR-268 enhanced human capabilities by providing precise measurements that operators could use to guide their decisions. Neither approach was inherently superior. Both worked within their respective technical and doctrinal contexts. The modified SCR-268 succeeded because it matched British operational doctrine, which emphasized skilled operators working with capable equipment rather than automation replacing human judgment. The statistical record of modified SCR-268 performance through the summer of 1944 provides quantitative evidence of its effectiveness. Between July 1st and August 31st, anti-aircraft guns equipped with modified SCR-268 fire control destroyed 2,347 V-1 flying bombs out of approximately 4,500 that entered the coastal gun belt, a 52% kill rate. The ammunition expenditure averaged 2,100 rounds per kill, representing a 5-fold improvement over the pre-modification period. Perhaps most significantly, night kills accounted for 44% of the total, demonstrating that darkness provided no protection for flying bombs against radar-directed fire. These numbers translated directly into civilian casualties avoided. Each V-1 that detonated in central London killed an average of 4.8 people and injured approximately 35. The 2,347 flying bombs destroyed over Kent represented approximately 11,000 civilian deaths prevented and over 80,000 injuries avoided. The modified SCR-268, created through unauthorized equipment modification by a civilian engineer working outside normal procurement channels, had saved more British lives than many conventional military operations. The technical community's reaction to Strang's work revealed interesting tensions between innovation and orthodoxy. Official reports compiled by the SIDARs Ministry of Supply acknowledged the modified SCR-268's effectiveness, while carefully noting that the modifications violated normal engineering standards and could not be recommended for general adoption. One report, written in September 1944, stated with bureaucratic precision, "The modifications to SCR-268 radars employed in Operation Diver achieved remarkable operational success through methods that cannot be endorsed as standard practice. Equipment operation beyond design specifications risks catastrophic failure and cannot be approved for non-emergency applications." However, in the specific context of V-1 defense, where alternative solutions were unavailable and the tactical situation demanded immediate action, the modifications proved both necessary and effective. This carefully worded assessment captured the fundamental dilemma faced by military technical authorities. Strang's modifications worked, saving thousands of lives and demonstrating engineering insight of high order. They also violated every principle of conservative engineering practice that normally governed military equipment. Approving them officially would establish precedent for unauthorized modifications that could lead to disasters in less skilled hands. Condemning them would be unconscionable, given their life-saving effectiveness. The bureaucratic solution was to acknowledge success while carefully limiting the precedent. Louis Strang himself remained remarkably modest about his achievement. In a technical paper written after the war for the Institution of Electrical Engineers, he described the modified SCR-268 as simply making existing equipment perform the mission it was capable of performing if operated without artificial limitations. The original design, he argued, had been constrained by conservative assumptions about operator skill and peacetime reliability requirements that were inappropriate for wartime emergency conditions. Removing those constraints allowed the committee radar to demonstrate its actual capabilities rather than its bureaucratically limited specifications. This perspective revealed a fundamental insight about military technology. Equipment designed to meet peacetime specifications often contained capability margins that could be exploited in emergency conditions by skilled operators willing to accept increased risk. The SCR-268 could track faster and measure more accurately than its rated specifications suggested, because those specifications had been set conservatively to ensure reliability under all conditions. Operating at the equipment's actual physical limits, rather than its rated limits, extracted performance that designers knew existed but had deliberately restricted. The Germans never fully understood what had defeated their V-1 campaign. Intelligence reports compiled by Luftwaffe headquarters attributed improved British anti-aircraft effectiveness to increased gun deployments, better fighter coverage, and improved ammunition. The possibility that Americans had provided obsolete surplus radar that British engineers had modified into highly effective fire control systems apparently never occurred to German analysts. This intelligence failure reflected broader German assumptions about Allied technical capabilities that persisted despite mounting evidence to the contrary. Major General Walter Dornberger, who directed German long-range weapons development, including both the V-1 and V-2 programs, wrote after the war that the V-1 campaign's failure surprised him completely. "We calculated that British defences would destroy perhaps 30 to 40% of our flying bombs, based on their demonstrated capabilities against manned aircraft. Instead, they achieved kill rates exceeding 50%, using fire control methods that our intelligence never identified. We knew they had radar. We did not understand that they had developed radar-directed anti-aircraft fire to such effectiveness. By the time we recognized the situation, the campaign had already failed. The modified SCR-268's success influenced American fire control development in ways that became apparent only after the war. Engineers at Bell Laboratories, learning that their supposedly obsolete radar had been successfully modified for V-1 defense, conducted detailed analysis of Strang's modifications. The technical reports they produced influenced the design of post-war fire control systems, particularly in the area of operator interface design. The recognition that skilled operators could extract performance beyond designed specifications if given appropriate controls led to more flexible control systems in subsequent radar developments. The SCR-268 continued in operational service well beyond the V-1 campaign. When Germany began launching V-2 ballistic missiles against London in September 1944, modified SCR-268 radars were used to track the missiles during their brief radar-visible ascent phase. The data collected contributed to intelligence assessments about V-2 performance and launch locations. Though the missiles themselves could not be intercepted, the tracking data proved valuable for targeting Allied bombing campaigns against launch sites. After the war ended, many of the modified SCR-268 units were retained in British anti-aircraft defences, rather than being scrapped as obsolete equipment. The radar's proven effectiveness and the British operators' familiarity with its capabilities made it more valuable than newer systems that would require extensive training to use effectively. Some units remained operational with British anti-aircraft regiments until the early 1950s, when the advent of jet aircraft and guided missiles finally rendered the old radar truly obsolete. Lieutenant Robert Turner, whose battery achieved the first V-1 kill with modified SCR-268, survived the war and remained in British military service until 1952, in his retirement memoir, published privately. And in 1968, he reflected on that June night when Louis Strang's unauthorized modifications proved themselves in combat. We had assumed that obsolete equipment was useless equipment, that American surplus radar could not possibly match the latest developments. Strang proved that assumption completely wrong. He showed that intelligent modification by someone who understood the equipment's actual capabilities could create effective weapons from what others had discarded. That lesson, that innovation matters more than specifications, that understanding capability matters more than following manuals, remained with me throughout my career. The broader strategic impact of modified SCR-268 deployment extended beyond the V-1 campaign's tactical results. The German High Command had intended the Vengeance weapons campaign to achieve psychological effects that would compensate for military defeats on conventional battlefields. If British civilians could be terrorized into demanding peace negotiations, if the destruction of London could break British morale, then Germany might achieve through terror bombing what it could no longer accomplish through military victory. The failure of the V-1 campaign, with over half of all flying bombs destroyed before reaching their targets, eliminated any possibility that Vengeance weapons could achieve strategic significance. The resources Germany devoted to V-1 production and deployment represented opportunity costs that significantly impacted German military effectiveness. The factories producing flying bombs could have manufactured fighter aircraft desperately needed to defend German cities against Allied strategic bombing. The slave labour assembling V-1s second under brutal conditions could have been used in more productive ways. The launch sites required constant maintenance and defence against Allied attacks, diverting resources from other defensive priorities. When the V-1 campaign failed to achieve its strategic objectives, all those resources had been wasted on a weapon that proved incapable of changing the war's outcome. Statistical analysis conducted after the war attempted to quantify the modified SCR-268's contribution to Allied victory. The calculations were necessarily approximate, involving assumptions about what would have happened if V-1 defences had remained at their June 1944 effectiveness levels. The most conservative estimates suggested that modified SCR-268 radar prevented approximately 9,000 civilian deaths and 60,000 serious injuries during the summer of 1944. More speculative analysis argued that successful V-1 attacks might have disrupted war production and delayed Allied operations, potentially extending the war by weeks or months. These secondary effects, though impossible to quantify precisely, suggested that the modified radar's impact extended far beyond its direct combat effectiveness. The human cost of the V-1 campaign, even with effective defences, remained substantial. Between June 13th and August 31st, 1944, approximately 2,400 V-1s second reached London and other British cities, killing over 6,000 people and injuring over 17,000. Each successful penetration of the defensive belt represented a tactical failure, a flying bomb that evaded fighters and survived the gun belt to reach its target. The modified SCR-268 had transformed V-1 defence from nearly hopeless to reasonably effective, but effectiveness, measured in percentages, still translated to individual tragedies for those who happened to be present when flying bombs detonated. The technical lessons learned from modified SCR-268 operations influenced post-war military doctrine in ways that extended far beyond fire control radar. The most significant insight was that equipment specifications represented bureaucratic choices rather than physical limitations. Designers built margins into military equipment to ensure reliability under worst-case conditions. Those margins could be exploited in emergency situations by operators willing to accept reduced reliability in exchange for enhanced performance. This principle, that actual capability exceeded rated capability, became fundamental to military equipment development throughout the Cold War era. The organizational lesson was equally important. Louis Strang's unauthorized modifications succeeded because military authorities, faced with urgent operational requirements and lack of better alternatives, chose to prioritize results over procedures. In peacetime bureaucracy, his actions would have been condemned as dangerous improvisation. In wartime emergency, they were recognized as exactly the kind of creative problem-solving that wins wars. The tension between innovation and standardization, between individual initiative and organizational control, remains central to military effectiveness in any era. The modified SCR-268 represented American industrial pragmatism applied to British operational requirements. The radar had been designed by American engineers for American military doctrine, built by American industry using mass production techniques, declared obsolete by American technical standards, and transformed into an effective weapon by British engineers who understood that capability mattered more than specifications. This international collaboration, unplanned and largely accidental, demonstrated that Allied victory depended as much on flexible thinking and resourceful improvisation as on industrial production and technological superiority. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.